All right, folks, welcome back. And let's get to it. So today we're going to focus on more details about Android system and security features. So again, we continue this, quick check of all the different components and how all these things come together. And then I have also a bunch of slides on HTTP, HTTPS, and SSL pinning, which seem to confuse a lot of people, even supposedly expert and people in our community. Okay, so let's get to it. First thing we're going to focus on is web views and mobile web browsers. So what are these? And why are these security relevant and interesting to discuss? So a web view is basically, it's a particular type of view to display web pages. So as you should know at this point, you have a mobile app and it has activities and things like this. And each of these activity can be built with different widgets and things like this. Okay. And one of these type of widgets is the view. So view is some kind of I think is a class or an interface, and then you have different kind of views. And one of these views is instances of this views is the web view. Okay, and web view happen to be a view whose main task is to display web pages. So the idea is that once you have if you want to have a web view, basically you would take your application and then you would include a view in your app that is a web view. So a web view will be part of your application. Okay, and somehow it displays web pages, but it's not as a full-fledged browser. Okay, so you can display HTML, so you can see your own web page, for example, but you don't have all the features of an actual browser. Okay, so for example, there is no navigation control, there is no address bar, and so forth. But it is more customizable. So if you basically open a web browser, well, the web browser is a different application, but a web view is part of your app. So you have a chance to actually modify the lead a little bit and again, customize it. So that's the problem. One very, very, very important item to discuss when talking about web views is JavaScript. So basically, I said a web view is somehow something to render web pages. So it takes HTML, for example, and then it displays it, okay? But it can also be run to execute JavaScript like a traditional browser. And that's the way you do it. Basically, you first get a pointer, you get a reference to the actual web view, as you would do for any other view. And then we get the settings, and then we basically do the settings.set JavaScript enabled true. So this is what you need to do to enable the JavaScript functionality of the web view. And the idea or the power of this JavaScript in this context is that you can configure your app so that the JavaScript actually has code that can interact with core components of your own application. And this is not, if you know how JavaScript works in the web browser, in normal web browser, so you take JavaScript, it's executed in the web browser, and the web browser creates some kind of a sandbox, so you don't exit from there. But in this case, there are tricks to make this JavaScript code able to interact with the Java component of your application. Okay. So here is an example that's I'm going to show you how you actually can do it. So first of all, let's say you have a show toast method. This is Java code. And let's say that you want to have this show toast method available from the JavaScript. So somehow later on you want to have an HTML page which contains some JavaScript script, and then this JavaScript script should be able to call and invoke show toast method. Okay, so what you do is you take this show toast method and then you use this at JavaScript interface kind of notation. Okay, and then what you do is you take your web view and then somehow you can add a JavaScript interface, and that's how you do it. WebView.add JavaScript interface, and you call it in this case Android. And now from the JavaScript, what you can do is the following. For example, here you're defining a button, and you're saying, once you click on it, please invoke the show Android toast, which is a JavaScript method, and it's implemented here. Show Android toast. This show Android toast JavaScript method is gonna do Android.showToast with the toast message. And this Android, basically, that's the word here. That's the object that you define. And show toast is the actual Java method. So now from JavaScript, you can invoke Java method. Why am I making a big deal about this? Well, turns out that there are some scenarios where the JavaScript code can actually be controlled by the attacker. So think about this. When you have Java code for your own application, well, you are the developer, right? You take the Java code and then you compile it, and that's it. The Java code that you wrote is the one that is running within the application, and that's about it. Okay, unless you use crazy things like dynamic code loading and things like this. But by default, that's how it is. No other people can actually inject our other Java code there. However, with the JavaScript, there are more scenarios where this attacker interception can actually happen. So one thing you should always ask is, there is JavaScript, okay, but who controls it? Is it this JavaScript to HTML page actually fully controllable or controlled by the developer? For example, how is it retrieved? Is it something hard-coded in the app? If it's something hard-coded in the app, then the attacker cannot really modify it. So if it's just literally a file, then the application is going to read the file, execute the file, and that's about it. Okay, but there are other circumstances where this other piece of HTML or JavaScript is actually downloaded from the network. And then you have other questions like, how is it downloaded from the network? As we're going to see later on today, if you download something from HTTP, it's trivial for an attacker to actually modify the file that is being retrieved. And so at this point, the attacker can control the JavaScript that is run within the application. Now, if your JavaScript was normal JavaScript, like in a web browser, then it's still problematic, but at least there is the browser sandbox and so forth. But if you have one of these apps from which the JavaScript can actually control the Java part, then you may be in trouble, okay? So the point here is that if an attacker is able to modify the HTML and also the JavaScript inside, then she can invoke, execute the Java methods that are exposed, if there are any. If there are not, then it's fine. But if there are some methods exposed, then the attacker can actually invoke them. Again, I'm making a big deal about this because there have been real-world cases where this was a problem, and it's much more common to have JavaScript controllable code from the attacker with respect to Java control code from the attacker. Okay, because then you're basically interacting with the web, and depending if you are accessing the web in a non-safe way, then the attacker can actually win. Now, in the past was actually even worse. So in these slides, I presented that to make a Java method available from the JavaScript, you need to do this tag add JavaScript interface. But in the past, up to Android 4.2, which admittedly is a long time ago, like 6 years ago, basically this add JavaScript interface was not mandatory to add, to be able for a Java method to be available from JavaScript. So basically, if you had, if you worked with this old version of Android, JavaScript by default could access every possible object in your application, including framework APIs. Okay, so there were proof of concepts that were going around that were looking like something like this, where basically you could define an execute JavaScript function that, again, the attacker would actually inject in the target application, and then you could do something like this, basically playing with reflection. You could get access to the runtime object and then invoke a command, and then either invoke a shell command or get a shell within the context of the target application. Okay, so this was very, very problematic, and again, that's why the Android security team eventually decided, okay, you know what, by default, maybe JavaScript should not be able to access every Java method. Now we need to ask developers to explicitly say which Java method should be available, and the way you do it is to add this add JavaScript interface. Okay. So again, it was a big deal because people found bugs of this kind, where basically you could inject JavaScript in the network, and then some researchers were able to find some of these bugs in an advertisement framework, and that's pretty bad, right? Because you have advertisement framework that, as a developer, I embed in my own application, and this advertisement framework would be embedded, let's say, millions of applications, and each of these apps would actually be vulnerable to this attack, which would lead to remote code execution. Because if you retrieve, for example, a JavaScript or HTML resource with HTTP and not HTTPS, any attacker within your network path or on the same Wi-Fi then could access, can modify the JavaScript, and then through these tricks actually run a shell within the context of the application, and read all the secrets of the application, security tokens, and things like this. Okay, so that's why I'm making this a big deal. So whenever you see a web view in an application and there is this set JavaScript interface enabled, eyes out, because the app might be vulnerable. It doesn't mean it's vulnerable, but it's one of these features that should be handled with care. Okay, cool. Now, a bunch of notes about the security web view. So web view is actually a pretty complicated piece of code, right? Web browsers are some of the most complicated code we have out there. You have HTML, JavaScript, all these web technologies. They need to somehow, parse them and then render them and so forth. And it turns out there were many bugs, and it's getting more and more difficult to find these bugs. But historically, there have been many bugs there. And again, they're particularly relevant because this piece of code, code that actually processes HTML and JavaScript, is easily reachable by attackers. Okay, they just need to convince you to click on a URL and so forth. Okay, so web view is also very complicated because it somehow also has this feature of taking HTML, parsing it, rendering it, and so forth. And it happened that there are security bugs. Now, that's a security problem, but the biggest security problem is that this web view was somehow embedded in the application and in the framework. Okay, so it was a core component of the framework. And again, this is complicated code, so it leads to bugs and so forth. And the problem is that up to Android 5, this web view was a component implemented a big monolithic Android framework, which means that if you find a bug there, then it still remains unpatched unless somebody else patched it. Okay, but if something is a core component of the framework, it's actually more difficult to patch it, because then at that point I don't even think we had these security bulletins and these monthly updates. But you get the idea. It's not like updating an app where basically you can do it out of band. You can just say push a new version, and then through the Play Store you get the application updated. That's the required a full update of the entire Android framework. And again, slow update cycles create really big issues. And from Android 5, what they did was to basically break this web view into a separate app, which can be updated independently from the Android framework. So now, if you have your own application, then you can have a web view, but the web view code is actually implemented in a different app, not in the Android framework. And that means that when the Android security team finds a bug there, they can basically push a new web view application, and your phone is going to get it much, much faster compared to when you will need to wait for a full-fledged update of the Android framework. Cool. All right, so instead of actually embedding a web view, what you could do if your purpose in your application is just to just to have a URL, and then you want the user to be able to see this URL, what you can do is that don't embed a web view. You basically can do that once the user clicks on this URL, you basically open the browser, browsing to this specific URL. Okay, so you just open Chrome or whatever browser you install on your phone. So you don't need to have this targeted or specific component in your application. Yeah, so the way it's done is through intents. You basically send an intent with the action view, and the data, you set it to the URL you want the user to visit. So whenever you click on a link or you press a button or whatever thing you want, when your application sends an intent with this action and with this data, the app is gonna basically send this intent around, and then the framework is gonna say, hey, who can answer this intent? So the framework is gonna say, okay, the action is action view, and the data is something like this. And then the framework goes around and says, oh, which application can actually handle this action view and maybe data starting with HTTP or HTTPS. Turns out that Chrome, Firefox, all these web browsers or mobile browsers on your phone declare many activities, and one of which is intent filter for this kind of thing. And that's why they are triggered. And that's why once you click on a link, or once the app has a button to click on a link and the intent is sent, that's why this stuff triggers, the browser is open. Now, this is actually a common trick to bypass the intent information. So let's say that you have a malicious app that wants to leak information out, and you don't want to ask the internet permission, or for some reason you do not have the internet permission. This is a common trick to get out, because you can basically, nothing prevents you to send intents around. You can send an intent with this. You can put as a URL your own URL, and maybe in the get parameters, which are specified in the URL, you can put the secret you want to leak to the internet, and bam. Now, it's not super stealthy because the user is going to see that the browser is open, but maybe at that point it's too late. So depending on the attack context, this is actually a pretty good trick. And about this internet permission bypass, a little bit of more notes. Again, this is how technically you can do, how you can send data out. Again, it is not super stealthy. The other drawback is that there is limited throughput in a sense that you do this, but there is a specific length limit to the get request parameters. So it's not that you can leak megabytes and megabytes of data like this. Maybe you can send many, but it's not super stealthy. But the reason I want to discuss this is that this is an example of confused deputy. Second. This is an example of confused deputy. Okay, what is confused deputy? It's one of these big concepts that I try to highlight that are important regardless of mobile security. This is a big security thing. I try to do the same with defense in depth and things like this. So please, eyes out. That's a concept of security. You're going to see this in many, many different subfields of the security research area. So it's not specific to mobile security. So what is it? So confused deputy problem is the following. Imagine a scenario where you have a malicious app X that wants to perform action A, but it doesn't have the appropriate permission. So what you could do is to find an application Y that has the permission to perform action A, and maybe there is a way to ask Y, please, could you please perform action A on my behalf? Okay. And if you find an application Y like this, then you have the problem of confused deputy. Basically, the receiving framework, it receives a request, which in this case would be application Y asking to perform action A. The framework says, well, it's Y asking me to perform action A. Let me check. Okay, Y has the proper permission, so okay, I'm gonna let you do it. And the confused deputy problem kicks in because the actual request was started from X, not from Y. And the framework doesn't know this, and so it's confused. So I keep stressing this point because there are several classes of vulnerabilities, which we're going to see later, that fall under this umbrella. So again, it's not one bug; it's a concept, it's a category of bugs. Okay, is whenever there is a security check, and the framework or whoever does a security check somehow is confused, and it doesn't know that the actual request and the actual component that would benefit from this request is not the one that seems to ask for, but is another one. Okay. One question could be, it's a confused deputy problem. It's a bug class. Why doesn't Google fix it? Well, it would break a lot of things, and that's one of these trade-offs, right? It's a way to bypass the internet permission, but it's not catastrophic. The internet permission is also a normal permission, so an app can actually just ask it, and nobody's going to be alerted anyways. And it would, if you stop this, it would break the basic component of sending intents around and so forth. So it's considered by design. It's not going to be fixed. And again, it's also important to not just bash Google. Oh, this guy didn't want to fix it. That's not the point. The point is that when there are bugs, for some kind of bugs, there are always important trade-offs that you need to consider. And in some cases, it may not be appropriate to just fix the bug if you cause crazy amount of other problems. Okay, there is always a trade-off, or in many cases, there is a trade-off that you should be considering. Cool. Some notes on web browsers. All right. So as I mentioned, JavaScript is code that can run within the browser. And we have multiple browsers: Chrome, Firefox, Edge, Safari, Explorer, etc. And conceptually, the browser implements a sandbox. So what does it mean? Again, it means that I download the JavaScript on my laptop, so Chrome. So Chrome downloads this JavaScript from a web page, and then Chrome takes this JavaScript, parses it, and understands, this JavaScript is asking me to do this and this and this, and execute it. But this JavaScript doesn't really have the power to escape from the browser context. So it can do things, it can do set cookies, it can access to some private file system inside the browser to store some data, but it cannot read the file on my real file system. Okay, it cannot interact with other processes around. It cannot leak all my keystrokes and things like this. Okay, I mean, actually, a web page could actually leak the keystrokes that you are typing in this specific page, but you cannot do this on, if you type on your notepad and so forth. So there are limitations, and that's when the sandbox keyword kicks in. Okay, another aspect of the sandbox is, for example, that you have a web page google.com, and then I have another page from peppapig.com, and the peppapig.com maybe is a malicious website, and if there is JavaScript, the JavaScript is confined to the peppapig.com. It cannot just, can I please read things from google.com with the cookies and so forth? You cannot do this. Okay, there are rules in place. That's a web security thing. So we're not gonna go in depth into this, but you need to get the point. There is a sandbox and there are rules that should be respected. With that being said, in modern browsers, JavaScript has access to a number of APIs. Okay, and I've listed here some of them. So somehow you can, there are APIs that can access to the motion, so motion data like acceleration, rotation, orientation, or proximity. Or there was some APIs about ambient light, so you can access, you can get an idea of how much light there is around. And then people found attacks to to abuse this kind of APIs, and other researchers found that advertising frameworks and things like this were actually abusing these APIs to leak personal information, or to fingerprint the users and to track the users, even if they didn't know it. And so eventually some of these APIs have been deprecated, and now they're not available anymore, or the sensibility and the precision with which they return data is actually much lower. Okay, so keep in mind that there is a sandbox, but there are some APIs that through which you can access, you can interact with external world, and depending on the context, this may be a problem or not. Cool. All right, so we are changing topic now. Again, we're going to explore another big security related thing about Android, and it is accessibility service. It's one of my favorite topics. I had several works on this, so it's quite interesting. So let's get to it. So accessibility service, or A11Y, is a shortcut, is basically a mechanism for apps to assist users with disabilities. Okay. What does it mean in practice? Well, an app, basically, you can say that it can act as an accessibility service. So somehow, I'm going to show later how you can do it, but an app basically can say to the system, I would like to be an accessibility service. Okay. And, you need to go through some permission request. Once you are an accessibility service, you have many powerful capabilities. For example, you can be notified for every UI event on your user interface. Okay, there is a new button being drawn, you know it. There is some text being, written, then you know it, and you know actually the text. Okay, yeah, you know when the user is clicking on something, and so forth. You can also be an active component. So basically, once you're an accessibility service, you can decide to click somewhere, or to fill a text widget with some an edit text with some text. Okay, so you can actually programmatically interact with the user interface. And again, it's very powerful. And the idea is that if you are an accessibility service as an app, you can basically help a user with disability. Maybe the user doesn't really see well. So what you could do, if you are an app like this, is to somehow automatically understand what kind of text is drawn on your application, and then this application would actually, tell it to the user. with sound. Okay. Another use case that I've seen, that I've heard of, is that there are some, some people with disabilities, they cannot really type easily on their phone, so they can attach an external device, and that this external device may actually be communicating with, an application on the phone that acts as a accessibility service, and this application can actually automatically interact by clicking around, by entering text, and so forth. Okay, so it's an extremely important component. Turns out that many popular apps use it. And we did a study on this aspect. And it turns out that in our study that of the top apps that were using this, none of these apps were actually using it to help people with disabilities. They were using this as a shortcut to be able to programmatically interact with the user interface. Okay. Or for example, understanding if you're an app blocker, you want to understand, is the user interacting with application XYZ? Now I block you. Okay, again, how do you know if the user is interacting with application XYZ? Well, when you go to application XYZ, there is a new UI event and the accessibility service will be informed. Okay, so if you are an accessibility service, you actually have a lot of information and you actually have a lot of power because you can actually do things. And so somehow it is not strictly security related, but given the power that it has, of course, it becomes security related. As every other things, every powerful mechanism that could be abused becomes security related. Okay. So it's very powerful. So there are several security mechanisms to prevent abuse, and let's get to some of them. The first one is that it's complicated to get access to it. It's not that you just put the user's permission something, but you need to go through a multi-click steps to actually get the permission. So somehow you need to say in the manifest, I would like to be an accessibility service, and then you need to ask the user to please go through the menu and enable it. And to enable it, again, is a multi-click step. You basically will need to find your go to accessibility settings, and then your app will be there. The user needs to click it, and then basically the user needs to click on the on button, and then the user would actually see a pop-up with information, and he's saying, this application may actually observe your actions and then retrieve window content and so forth. So somehow the user is actually informed that this mechanism could be very powerful. And after the OK, now you have a CBD service. So multi-click setting. The second security mechanism is, or I would say was, as it's going to be clear later on, that accessibility service in theory could not read sensitive information from the screen. For example, password fields. And this is a quote from the documentation at that point, at least. And it was saying basically that since some events could contain privacy or private information, such as a password, basically any event fired in response to a manipulation of something like a password does not contain the text of the password. And at that point, it actually was true in the sense that if you have the text, which is a password, and you try to type it, then you will get the events. The user is modifying this, but you will not get the actual content of the password. Okay, so it's going to be a bit clear later on why I am kind of discussing this like it was like this, but now it's not like this. We'll see later. Okay, cool. So how are people, there are these security mechanisms. How are people actually getting this? Well, the first attack is to rely on people's stupidity. Find an excuse to require it and ask the user. And turns out this stuff still works. Okay, you just need to, if the user downloads an app and you can convince him the app is legitimate, then after a while you can ask him, you know what, you want to unlock this specific object from your game? I need a CBD service. And so, the application will contain a mini tutorial on why you will need this. You can just, it could say something, weird to convince the user that, I really need it, but this is not a big deal. And some users fall for it. And after this, basically, the app is a CBD service. They can do a lot of damage. The second attack is from one of my old papers, Cloak and Dagger. Basically, in this paper, we found several ways to actually get access to the CBD service. And one of these attacks was clickjacking. And the idea is basically that you convince the user to click somewhere, but this click is actually not going to the button the user is seeing, is actually going on below, and below maybe there was the OK button to enable a CBD service, and bam, we win. And the application, the malicious app actually has CBD service, okay? So this specifically jacking attack on the against the CBD service is not there anymore. It has been patched, but that's how we did it. And there is a link to the paper. There is a demo link there. But I'm gonna have a session later on in the class on UI security, and that's where I'm gonna discuss more in depth what this clickjacking means, why it was relevant at that point, how it was fixed, what's the current state with clickjacking, and so forth. So on this, of course, is a topic that I really like a lot, and I'm gonna postpone the details to the UI security session. The second thing we found for the paper is that there was a way to actually leak the user credentials. So again, documentation said if you modify the password, you shouldn't be able to see the password, but we found a way to actually get it. And again, I'm gonna go in the details later on how we actually did it. The mini spoiler is that sure, you don't see the password, but whenever you enter the password, you're actually interacting with the keyboard. What is the keyboard? Well, the keyboard is another application which has a bunch of buttons. Turns out, yes, you cannot read the password from the edit text. So if I type Peppa, I don't see Peppa, but I can see the user pressing on the P button, on the E button, the P button, and so forth. So by just tracking which buttons the user was interacting with on the keyboard, I could leak the password. So again, we're gonna go more in details later on UI security session, but the quick spoiler, basically we disclosed these bugs to the Android security team. This was already 4 years ago, and it was quite interesting. At the beginning, they told us after a month, nah, we're not gonna fix it, it works as intended. And then, I complained because I said, no, check the documentation. There is written I shouldn't be able to do it, but I can do it. So, and I marked it as high severity. And at that point, I was a PhD student, very poor. High severity bug, it means I basically doubled my net worth. Like, was it $1,000 or something? After a while, however, we got another message that I received with profound disappointment. Won't fix, because limiting the services would render the device unusable, which for me was quite interesting, because is it a bug or not? And again, that's when I encountered probably for the first time concretely the actual trade-off. There is always trade-off, and sometimes they're going to refuse to fix a bug or to acknowledge that the bug exists by saying that it will create too much damage to the benign application to actually fix it. And so we had a long discussion about this, and eventually they did not fix it. I think this bug is still there, and it works out. But it is what it is. Then later on, I complained again and said, guys, but check the documentation. It's still it says something, and now I can do it. And then eventually they reply with, we will update the documentation, which was super funny at that point. And the amazing part is that they actually did. So I checked, and there are two links here. On this, the first one, you're going to see the link to that page where the security note was still there saying, oh, you are not going to be able to leak the passwords. And then there is the current version, which basically is the same, but this security note just disappeared silently. So it was an instance of patch documentation, not the code. Super funny. I tried to request a CV for finding a bug in documentation. It did not work out. So yeah, my net worth at that point did not double up. Very sad. Cool, just a funny story. All right. Again, we're going to have many more details on RCBD service and clickjacking attacks later on the road. And now I would like to move on yet another topic, which is password managers and out-of-field frameworks. So what are these? Well, password manager in general, I hope you guys are aware of this. There are some kind of browser extensions or things like this that basically save your passwords, okay? So that once you go on facebook.com, the browser extension remembers, I know the password for this, and now it auto-fills it, and now you can click OK, and you're logged in Facebook. You don't need to enter it. And most people think that one of the advantages is that Once you have a password manager, you can put a random password. You don't need to remember it. That's, you know, it tries to discourage reusing the same password all over the place or small variations of the same passwords all over the place. So if you have a password manager, you don't need to remember. You just put some random string. The password manager remembers it for you, and that's it. This is, of course, a great advantage, but at least for me, the biggest advantage of password managers is that it prevents phishing attacks. Again, we're going to have slides and in details later on phishing attacks, but it's such an important point. I want to make it now. Phishing attack is where you have a page that tries to say, hey, I'm facebook.com, but it's not facebook.com. Okay, so it tries to mimic the Facebook UI, and it asks you, please put your username and password here. Now, if you don't have a password manager, and if you somehow fell for it, you're going to take your password. If it's secure or not, doesn't matter. And you're going to put it in this fake Facebook page. Once you click yes, the attacker has your password. If you rely on a password manager, you cannot fall for this attack. Why? Because the password manager knows that this password is for facebook.com. And so if you go to a website that is maybe facebook.com with the zero instead of the O and you don't notice, the password manager will absolutely refuse to put the real facebook.com password in the fake Facebook website. So somehow, the fact that the password manager doesn't automatically trigger and you cannot put the password there is going to be a big warning sign for me to say, okay, maybe this is not the real facebook.com website and I don't fall for the phishing attack. Okay. So remember this, it's great for phishing attacks and other many things. So big supporter of password manager. Okay, let's close up this parenthesis. Now we focus on mobile password managers. You have password managers also mobile. Okay, so if you are on a web, same stuff on the browser extensions, and now it's basically embedded in Chrome, for example. On a mobile app, well, see this UI. This is the Facebook application, and it asks you for username and password. And sure, you could basically open the password manager that you have in the web browser and then copy paste the Facebook password and put it there and log in. You could do this. But prominent password managers developers actually start to have the mobile version of it, so that the mobile app, the mobile version of it could actually say, aha, you are on Facebook, app, let me give you username and password in your Facebook app. Okay, so, and now I would like to explain how they work. So once you go to the Facebook app and you have a password manager installed, in this case is LastPass, you're going to see a pop-up like this. You know what? I have a password, save for facebook.com, and do you want to put it to this application? Click here. If you click there, then username and password are put in the mobile app. Okay, and then you can log in. Great. How does it actually work under the hood? And again, this is going to be important for how we actually break it. So the first one is accessibility service. Ta-da! So the trick is that you can build a mobile password manager through an accessibility service, because once you're an accessibility service, you can know which app the user is currently navigating to. And if you detect, okay, it's Facebook app, then you can take the user name and password, and you can automatically inject them to the mobile app through accessibility service, and that's it. Okay, so that's one trick that you can use. The second big component or technique is through the autofill framework. So the autofill framework is a new thing from Android 8, and somehow it's is the correct way, let's say, of implementing a mobile password manager, and it works in this way. So a password manager app can act as an autofill service. You specify some things in the manifest, you specify some things in your application, and so forth. And the idea is that a callback is invoked whenever the user visits a fillable activity. So now you have an activity like a Facebook app, and you can have a flag that says fillable. And if the user goes to a fillable activity, then the password manager is going to receive a callback saying, hey, you know what? The user is currently on a fillable activity. Do you maybe know how to help him? Do you know the password relevant to the specific activity? And so the package name can retrieve the password manager can retrieve the package name of the target application, and somehow can say, okay, I know this package name, or this should be the real Facebook application, and Facebook application, facebook.com, great, here is the password. Okay. And given this package name basically decides how to suggest the which password to suggest, if any. The third technology is OpenYOLO. OpenYOLO basically it's a kind of a protocol / framework to store, update, and autofill credentials. It's different technique in a sense that the target app, so for example, the Facebook application, will need to be modified to include the OpenYOLO client, and then this OpenYOLO client would talk to the OpenYOLO server on the phone, and then it would ask, hey, that's OpenYOLO client. I am Facebook application. Can I please get the facebook.com password? Yes, thank you very much. Okay, so it's a kind of a different technique, and it's open source. It was led by Dashland and Google. I did not see much adoption, so I don't think it's going to happen in the long term. But for completeness, I presented it. Okay, so with the diagram, it works like this. As I mentioned, there is OpenYOLO client, and then there is a credential provider. It's a kind of a server, and so is the client that asks, hey, can I please get the password? And if any, then the server says, okay, here it is. And now the application, since this is called by the developer, can actually automatically get the answer and put it in the username password thing, and maybe automatically click on the login button. Okay. Cool. And these were the three. The interesting part is the following: that in all three cases, accessibility service, autofill framework, and OpenYOLO, the main starting point to understand which app am I talking to and which kind of website credential should I give to this application starts from the package name. So somehow they always start from the package name to then map a package name corresponds to these credentials, to this, Facebook for this website. So for example, you have the real package name of Facebook is con.facebook.katana. And then somehow they are able to understand, hey, this is the package name for Facebook, or it looks like it. We're going to provide the credentials from facebook.com. Okay. So if you understood something or what I've discussed so far, you may, realize that trusting a package name may not be the best idea. In a sense, package name on a Play Store, con Facebook Katana, there can be only one, fine. But it's not that all the things that look like Facebook are actually Facebook. And so I hope that at this point you will say, really, they were doing this with our passwords? And you will scream in horror. Okay, so let's dig a bit deeper on what these guys were actually doing. So, you go as a user, you go to the Facebook application, and somehow LastPass shows this. And the question that should pop out in your mind is, how can they know that this specific application is associated to facebook.com? So in this case, it's the real Facebook app, maybe, and it's con Facebook Katana. And so maybe one can have a map like, con Facebook Katana maps to facebook.com. You could do this. And in this case, it wouldn't be super secure, but it would be actually quite secure, in a sense that it could be that if you download a bad con Facebook Katana application from a third-party market, then of course you will be, it's a malicious app, and you will be able to steal this password. But if you are dumb to install a fake Facebook application with a fake package name, you're going to lose your password anyway, so it's not very relevant. The point is that, unless they really have a strong map like con Facebook Katana maps to facebook.com, then you may be in trouble, depending on what kind of rules they actually use to map a specific package name to a specific domain name. And again, maybe with Facebook, this problem seems trivial. You just hard code it Facebook, right? You can do this with Google. You can do this with many other things, but it turns out there are many applications out there, and there are many websites. So what do this guy do? Somehow, they have some complicated way to do this. Before we go to this, one other point I almost forgot to say, that this step of recognizing who are you talking to is trivial for browser password managers. Okay, so on Android, you have this package name component and abstraction. You need to map it to a domain name abstraction. If you're in a browser password manager, this step is trivial because there are no package names there. You go to a website, and the credentials were born from a website. So there is no kind of mapping to be done. Okay, if you go to facebook.com, I give you credentials of facebook.com. In this case, it's complicated because we go to the application and somehow should be linked to facebook.com. And now I need to remember, okay, this was actually related to facebook.com. Okay, this should be, it's very important to remember this. So again, package name cannot be trusted. You can trust com Facebook Katana on the Play Store. You know it's the real Facebook, but nobody's checking or vetting package names in general. So you should not assume more things than the actual assumption you should make. So again, you can trust com Facebook Katana, but it's not like the web, like where Facebook.com, a legitimate website. Can I get domain name peppa.facebook.com? No, I cannot. But on the word of package names, I can actually do this. There is no trust relationship between a package and a subpackage. Again, on the word of domain names, we have this. Facebook.com somehow controls peppa.facebook.com, but Facebook, com Facebook Katana does not control anything on com Facebook Peppa Pig, com Facebook Katana, whatever, and so forth. Okay, so it's extremely easy to just submit an app on the Play Store with a package name like this, and we did it and we got it. So at that point, we had a package name, an app with a package name con.facebook.ebook. Extremely simple. Okay, and the problem is, this is not a big deal. The problem is when password managers rely on these fake and inexistent trust assumptions to actually do the mapping, and that's where the cool part kicked in. And so we analyzed a bunch of, that's another paper of ours from a couple of years ago. Again, super fun work. We checked a bunch of famous, let's say, password managers. And then for each of these, when we try to understand how are they doing this mapping, it's a complicated problem. So we checked Dashline, and we found out that these guys had heuristics to infer the mapping from the package name in a way that it was, shocking, let's say. What they would do is the following. They take the package name, then they split it across the dot, so it would have different components, and then it would check for each component if at least 3 of its characters are contained in a website field in each entry in the Dashline database, then they would suggest this to the user. So for example, if you have a package name called xxx face YY, this would trigger a match with facebook.com, because it will get xxx face YY, and then it will see, oh, face actually is a substring longer than 3 characters of facebook.com, and this may be a match. And again, this attack worked quite nicely. We actually did another attack where basically you could have an app with com instlin ube, and you will get credentials for these websites. Okay, so it's very generic. You can select which specific credentials you want the user to see. We also check LastPass, and it was different. They basically had a heuristic to infer the mapping from the package name in a way that this really focusing on exploiting or using the trust assumption that this does not exist for package names. So what they would do is to get the package name, they would flip it, and then they would check if, so for example, you have com Facebook Katana, they would flip it, and now you have katana.facebook.com, and then if one of the credentials are associated to a domain name, which is a suffix of the string that you have, then it will be proposed as it will be suggested as a, do you want to put this password there? And so in this case, you would have com Facebook Katana. This will become katana.facebook.com. This matches with facebook.com, and then LastPass will propose to the user, hey, this seems Facebook. Do you want to put the username and password? One important note that I need to make is that this attack is not automatic, in a sense that if the password manager is fooled to believe that this is Facebook, the password manager just suggests to the user that this could be Facebook, and the user needs to click yes. So the attack is not automatic. Our point was that, this kind of bug helps be the case for the attacker to convince the user that this is the real Facebook application. Because, if you have an app that pretends to be Facebook, and now you also see, and so the user is already uncertain, and then you see a LastPass saying, hey, this seems facebook.com, do you want the password? It's much more likely that the user falls for it, with respect to a case where the LastPass wouldn't try to ease this step. Okay, cool. So again, for this, we had an app called com Facebook Evil, and then this would trigger a suggestion for facebook.com. Easy peasy. The other thing that was interesting is that we found that LastPass had access to some kind of a crowdsourced mapping, where basically, we found this map downloaded from a JSON from one of their backends, where basically there were tons of these package names associated to some random, some domain names. And they were very weird. There were some kind of local IP addresses, internal IP addresses, things like this. And it was clear that this was crowdsourced. So at that point, what you could do is to say to LastPass, if LastPass didn't have a good suggestion for this, for this package name, you could say share my finding or share my association with the community. And then you could do this. And then one potential attack would have been to somehow spray this crowd mapping to submit tons of these submissions so that the attacker application Peppa Pig would be associated to Facebook.com, regardless of the other heuristics that one would use. Okay, we didn't do this attack, of course, because it could have affected actual users, but it was a potential theoretical attack we had in mind. Another password manager we checked was Keeper, and again it was a different technique. Very interesting. So what these guys did was to take the package name, and then they were basically querying the Play Store. So what does it mean? If you go to the Play Store to get information about an app, you will see that the URL is something like play.google.com, and then there's $ID equal, and that's the package name. So from the package name, you can get the URL of the Play Store page, the website that contains information about the application. So what these guys would do was to build the URL, download the page, and then they would actually parse out the visit website. And this would be the one website associated with the specific package name. Of course, again, you should scream in order at this point if you understood anything about what I'm talking about, because of course the visit website is not trusted item. I could put, my website is this Facebook page, facebook.com/my page. And this would be used to link my package name, which could be whatever, literally whatever.com, could be linked to facebook.com. Why? Because my website points to a Facebook page. Okay. So another, this was the tree that we checked. It was super interesting. Another thing that we found is the following. Let's say you have something like this, and now let's say the password field is not there. Okay. So it turns out that, so what we try to do is to have a malicious app where basically we just show the username, but not the password. The password field is still there. We just make it invisible. We could make it invisible with a number of tricks. We could have a field that is 1 by 1 pixel. We could make a field where the foreground color and the background color are the same. So it's there, but you don't see it. We can make it literally invisible by setting the flag, or we can move it around the screen so that the user doesn't see it there, and so forth. And the question was, how would Password Manager react? Turns out that Password Manager would react the same way. You will see the pop-up, you press the button, and now both username and password are filled, even if the user cannot see the password. And again, the attack is not automatic, but of course the user would lower their bar of attention, let's say, if the app is just asking for the username, not for the password. Okay, so again, that's why we thought this attack was cool. Again, there are a number of ways to make the hidden fields, and this was just an overview of this research paper. And there is a link to the paper. It's already a couple of years ago, and we thought it was quite interesting. We collaborated with all these password managers. They fixed these bugs. They were super friendly and super good teams, and it was a fine experience. Okay. Cool. Still for this paper, we did something else that was not related to the password managers, but it was about the instant app. So I'm going to use this to explain this instant app and why, again, it's a feature of Android, but becomes security relevant. So what about instant apps? So in newer version of Android, you may have seen this already, where you can go to the Play Store and then you have a button that is try now next to the install. What is it? That's basically the instant app trigger. Instant app basically allows a developer to upload a subset of your application as an instant app. And the idea is that the developer can associate a specific URL. So okay, the idea of this subset is that basically you can tell the user, you know what, you don't want to install this 300 megabyte of stuff, you just want to try it out. Then basically you click try it out, and this application, the subset of the app, the small one, is downloaded and installed silently. And so the user can play with it And if he likes it, then he can do the actual installation. Okay, so it's a way to tease the user, hey, you want to try this, some kind of low effort thing without installing an application. The other thing about Instant App is that a developer can associate a specific URL to the Instant App. So in a way that if you click or if you go to this specific URL, it will trigger the prompt, hey, there is an Instant App associated to this URL. You maybe want to install it or try it out. And I think I have an example. Yes, the point is that you can try it out. Let's see if I have an example. Let's say that you go to this ultimateguitar.com. These guys actually had a legitimate application linked to this link. And basically you would have a pop-up at the bottom where you would say, hey, you know what? Do you want to open the app? If you click on it, basically it will trigger the Instant App installation. You're not really installing the full application, but somehow the system is internally installing an application without listing it properly as an application installed, okay? There are some constraints, but that's exactly what's going on under the hood. So the Instant App is loaded, and then bam, now you are within the Instant App, which is a subset of the real application. So basically you can play with it. It doesn't have all functionalities. If you really like it, you can press the install button, and then you will probably go to the Play Store page with the actual application, and then you can install it, okay? So get the idea. The key point that we tried to bring up in this paper was that, very cool, but once you have an Instant App installed on the system, then the attacker has full control of the user interface, because any app actually has full control of the user interface. Nowadays, you cannot override the bar at the bottom, you cannot override the bar at the top, but you control every single other pixel, okay? And in this case, of course, it's super benign, there is no problem, but this could be abused for sophisticated phishing attacks. And that's where basically this Instant App trick kicks in. We somehow, that paper that I showed before, it was not focused on password manager, it was focused on having phishing attacks on modern versions of Android. And so we showed how this password manager, of course, make it easier for attackers to mount phishing attacks. And there's an irony that on the browser world, non-mobile browser world, basically password managers protect you from phishing attack, while in mobile that actually is the phishing attack. And then we also bring in the instant application to show how you could do end-to-end phishing attacks with a few clicks. So for example, let's say that you go on this website, and the idea for this scenario is that the website is actually malicious. It's try to, some kind of weird website. And then there is a PayPal button, okay? And then you click on the PayPal button, and you will go to something like this. There is a pop-up here. Note here, there is an open with, it will be the name of our application. Now, the interesting part here is that in theory, there is an icon here. Why there is no icon here? Because when we submitted our application, we basically put the icon to be a gray box, so you don't see there. Of course, you can put an icon that somehow resembles PayPal, but maybe Google is going to catch you. So that's why we did this trick, and just another trick to show that, hey, you can actually hide your real identity. And once you click on the open up, again, this is our logo, which was a gray square. Once you click on this one, basically you go to the Instant App application, and then bam. At this point, this is our malicious application, it's not the real PayPal. And somehow we can convince the user this is the real PayPal application. We can convince it easier because LastPass or any other password manager at that point kicks in and says, you know what? This seems like PayPal. Do you want to put your username and password? And again, this was not the real PayPal application, was something called compaypal.evil. That's just a random example that would trigger the recommendation for paypal.com. Okay. I want to conclude this part with, there is the right way of doing this. So somehow I kept talking about, these people use from package name, they try to build a mapping, they go from package name to the actual domain name. And, this is bad. It's bad, it's bad, it's bad, it's bad. How are you supposed to do this? Here it is. So there is a thing called digital asset links, or DAL. And the idea, I think, is very interesting technology, and this will actually solve the problem. The idea is the following. A website can basically say publicly, in a standardized form, that apps signed by this certificate are okay. It's better to explain this with an example. Facebook is using that, and Facebook can declare, you know what, apps signed with this certificate are okay. I mean that they are associated really to Facebook.com, in this way. Basically, if you go to this URL, you will see a JSON like this, where it says, you know what? There is a package name, com Facebook Katana, and you also have the hash of the actual certificate signing this application. This is extremely powerful because now, if you have an application that says, oh, I'm really from facebook.com, what you could do is to go to this URL, facebook.com/.wellknown/assetlinks.json. Again, this is the format of where you should put your digital asset links information. If you go here, you get a JSON, and then you can check whether your application's package name is in one of these package names listed there, and whether the app is signed with a certificate that is also listed there. If yes, since we can trust the connection from us to facebook.com, why? Because there is HTTPS here. Since we can trust this, we know that this information is somehow trusted, which we know now we have a way to check whether this application is actually the real one or not. Okay, so this is very cool, and it actually solves the problem conceptually. Unfortunately, once we did the study a couple of years ago, it turns out that only 2% of domain names that we found, I think, from LastPass or one of these applications, only 2% of these domain names actually supported this, which means a password manager doesn't really have a way to go there and, on Facebook now you can do it, but you cannot do it for every other website. Okay, and again, we interacted with these password manager vendors. They were very professional and super nice people. And somehow what the way they fix the bug is that basically if they can verify that the target application is really linked to facebook.com, for example, then they say everything is good. Otherwise, they put a huge warning. They say, hey, you know what? Our app could not verify the legitimacy of this application. Are you extremely sure that this app is the legitimate Facebook application? Okay. And I think, again, it's not perfect, because if the user failed for installing this fake Facebook application, I guess it's going to fail also to put username and password. But at that point, I guess it could be game over anyways. And I think it's a good trade-off. Without this DAL technology, I don't see other ways to fix this problem. So again, yet another example of trade-off between security and practicality, and that's what they chose. And to the best of my knowledge, all these relevant password managers did the same. There is also another password manager called Google Smart Lock, is integrated in the latest version of Android. I do not have it enabled, so I actually don't know if it's still there or not. I know it was there once we did the study a couple of years ago. And I think the Google folks have some kind of a web form or a Google form, where as a developer, you can say, as a developer of an app, you can say, I would like my app to be supported by password managers. So can you please add this link in your database? And so you can fill this form, and then Google will know. In the paper, we asked Google to release this. I don't think that happened, and I don't know what's the status right now. I don't know if this mapping became public. I think it would be extremely beneficial if Google would make it public, but yeah, I don't know what's the current status. I don't know. Again, more details are in the paper, and I think there is a link in the previous slide when I showed this PDF, and that's about it for this specific topic. And give me a second. All right, and here I'm back after a bit of a break. All right, so moving on a different topic, we'll talk about notifications. And this is yet another one of these topics where it may seem that it's absolutely unrelated to security, but it's going to turn out that it is. So let's see what this is about. So notifications, I'm referring to what you probably have in mind already. So you are playing with your phone and then something pops up. It's a notification, okay? So I'm talking about those kind of notifications. And so, as you can imagine, apps can do this, can create some of them. And one of the security aspects is that, sometimes notifications can contain sensitive information, such as maybe the two-factor authentication token to log in on your sensitive website, like the bank and so forth. Okay. Turns out it's not the only security aspect that is relevant, but this is one of them for sure. And This could also be not only pins, but private messages such as WhatsApp and Signal and so forth. Whenever you receive a message, then you get a notification with the content of the message. Again, two-factor authentication codes and so forth. And turns out that not only an app can create these notifications, an app can also request access to these notifications. So let's see how it works. There is a thing called notification listener service. You can create a service that somehow tries to listen for notifications. And basically, when you want to do it, basically you create a service that receives calls from the system when new notifications are posted or removed. So it's not that you become the notification manager, but basically you register this service and you tell the framework, hey, you know what, I'm a notification listener service and I would like to be notified when there is a new notification. And so once you do this, basically the system, so the Android framework actually calls you and gives you the details of the notification. Of course, there are security checks to make sure that not any app can actually request this. And so the user actually needs to manually grant this capability to the app. And I like to discuss this notification example because this is not one of the traditional permissions. It's not like a dangerous permission, like the getting access to location where basically there is a pop-up and then the user needs to grant this permission, after which point the app actually has the permission, access to location. Here it's a different kind of thing, and I think it's very important to clarify this. So first of all, to ask the user to grant this permission, what you can do is to create an intent like this. And as you notice, this is basically an intent specifying action, but it's defined under the Android.settings namespace. So somehow this is not about getting this notification thing, but with this intent, you're spawning up a new activity belonging to the settings app, and you're going to the activity about enabling or disabling notification permissions for other applications. Okay, so this intent doesn't get you any permission. This intent just goes you to a specific view of the settings app. And the other thing you need to do after you do the previous step, so there is an intent, and then the user goes to the setting, the user can say, okay, allow notifications to this application. There is another thing that a secure app should do when it gets access to notification, and it is this. So in your service manifest information, so this notification listener service, you need to specify within the service tag Android permission by notification listener service. Now, I'm going to make a big deal about this because it's a very confusing point, and it shouldn't be that confusing, but there are reviewers in top tier conferences that still get this wrong. So I would like to be super clear about what this actually means. So I'm going to ask you in the exam, so please, eyes open. With this kind of entry in the manifest about specification of the permission, this app is not asking for the notification permission. This should have been clear already, but let me underline this. This thing in red is not asking for any permission. After you do this, your app is not going to have any permission more than what you had already. How do you get the permission? Somehow you need to spawn with an intent and activity of the settings app, and after this, then you can get notification access. But this does not really give you the permission in terms of Android permission, and certainly this entry in the manifest does not give you any permission. Now, we already seen this syntax where basically, the way you ask for permission is that you need to open a uses permission tag and you specify which permission you want to use. This, as you noticed, is not about this. We're specifying a permission within a service tag. We could have done this in activity tag or a broadcast receiver tag and so forth. And we already explored what this means, but let me repeat this. Putting Android permission and a specific permission in a service tag, this means that to talk to this service, the requesting app or the app that tries to talk to the service needs to have this permission. Okay, so now we are basically defining a service, but now let's say there is another app. Unless this app has this by notification listener service permission, this app cannot bind, cannot communicate with the service. Okay, now This is important because, the service, how can we know if an external app can talk or not to the service? Well, it depends if the service is exported. In this case, the service is defining an intent filter. And if you define an intent filter, by default, the exported attribute is set to true. Since here there is nothing saying exported attribute equal to false, then the default kicks in, which means the exported attribute is equal to true. So by default, if you don't put anything else, if you don't put this permission, any other app on the phone can interact with this service. Okay, and this is bad because the service may have access to the actual notifications, and we don't want that any other third-party app may interact with it and maybe unintentionally leak the sensitive access of these notifications. Okay, so I hope you're getting the point. The permission specification here is not to ask for a permission. You do this in different ways. This is to protect your service that is going to process the notifications, is going to be protecting this service from requests from third-party applications, potentially malicious. Okay, so this is a defense mechanism. It's not asking for anything. It means unless you have this permission, you cannot talk to this guy. And the interesting part here is that if you check the documentation, this entry permission by notification listener service is actually, I think, a signature permission or a system permission, which means that a third-party app that you stole from the Play Store cannot get under any situation this kind of permission. Does it mean that this stuff doesn't make any sense? No, it kind of makes sense. It means that if you're a third-party app, there is no way you can ask for this permission, which means there is no way you can directly talk to the service. The idea is that the notification service, or the notification manager actually has this permission. And so the notification manager is actually able to talk to this guy, okay? But not anybody else. I will be clear. I think I wrote, yeah, big warning, please keep this in mind. The app is not requesting a permission, is defending itself from other apps, okay? And again, I would like to underline for the last time, this by notification listener service, I'm pretty sure it's a signature permission, so you cannot get it as a normal app. Okay, so even if you send the intent to open the settings app, this is just specifying to the notification manager through the settings that, hey, you know what, this app should be allowed to get this notification. So please keep into account. But this procedure is not granting this permission to the app. Again, the permission is a signature one, so a normal app cannot get it. All right. I think I'm being extremely boring. I'm gonna move on. Cool. This is actually how we do this in code. So the first thing we do is to create a builder, and basically, it's quite verbose, but you can set the icon, you can set the title, you can set the content, you can set the style, blah 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 blah. So you can set the priority. So that's how we build the notification. And once you build a notification, basically you get an instance of the notification manager, as we show in the second box, and then we use the notify method. And note how we actually pass an ID, and then we do mbuilder.build to actually produce the notification. Okay. And again, each notification is identified by ID. And so what you can do is to refresh. After you do this, you can basically say, okay, delete this notification or refresh it, and so forth. So given this ID, you can have a map from this ID to a notification displayed, and so this app can manage its own notification even after the creation. Okay, cool. And now we go to another feature of this notification that leads us to another very important security aspect related to notifications. So this is the same example as before, but we're just adding here the red line, and we're doing set content intent pending intent. And we need to answer two things. First of all, why are we doing this? And second of all, what the hell is a pending intent? Is it just a normal intent? So the why is simple. Let's say that you create a notification, but you also want to specify what should happen once the user clicks on the notification. This happens multiple times, right? If you read a notification from WhatsApp, then somehow once you click it, that specific maybe channel or group is open. Who is telling a notification about this? Well, through this. So somehow there is a way, that is this one, to basically create a notification and associate an action to what the system should do when the user taps on the notification. Okay. And again, the way we specify and we convey which action should be executed is through a pending intent, which again is not just an intent, it's something more complex, which we're going to explain now. So how do we create this pending intent? Check the second box on the bottom. We basically first start with an intent, so the first line, and then see how we do this. Pending intent pend equal pending intent don't get activity, and then we pass the intent. So somehow it seems like a wrapper for an intent. Now it may seem useless, it's not, but we're going to see in the next slide. It may seem useless, but so far we basically take an intent as we have been doing up to now. So an intent specifying maybe an explicit intent, so specifying which component should be started, or it could be an implicit intent, okay? And then we create a pending intent that somehow contains this intent, okay? And again, it should be clear it's some kind of a wrapper, but again, if it's not clear what's the purpose of this, kind of makes sense. And I think the next slide should clarify this. So a pending intent, again, it's a different component than an intent, so there are two different things. A pending intent is a description of an intent and a target action to perform with it. So again, it's a basically contains an intent. The pending intent contains an intent. This intent specifies what to do. Okay, this makes sense. And this is where the security relevant aspect kicks in. So somehow a pending intent is not just a wrapper for an intent. Otherwise, we wouldn't make this big deal out of this. A pending intent, basically, if I have a pending intent, if I have application A, and application A creates a pending intent the way we described it, and now this application A sends this pending intent to application B. Application B, now that it has this pending intent, basically he has the right to perform the operation that I specified within the intent, as if I were the application A. So let's say that application A basically creates a pending intent, which wraps an intent that is an explicit intent for activity 2. And let's say that activity 2 is not exported. Now, if activity 2 is not exported, you may assume up to now that there is no way that another application can start it, and you will be correct. However, if application A creates a pending intent, wrapping an intent pointing to activity 2, and its pending intent is sent around to application B, now application B somehow has the right and has a way to interact with activity 2 of application A, even if it's not exported. So somehow the pending intent is not just a wrapper, is a wrapper, but is also carrying it together, some kind of a security thing that says, application B, take this, and you have the right to interact with a component specified by the intent inside. Okay, so that's why it's relevant, because basically we are passing around security material, or a thing that has security access to something inside that should not be accessible from outside. And this, of course, there are apps that screw it up, but first of all, I would like to provide an intuition of why the notification system is managed like this. The why is that basically you create a notification and you associate a pending intent to it, and so when the user clicks it, whoever handles this notification, there is a pending intent, and whoever gets this pending intent, in terms of processing the notification tab, he has the right to start any activity or any component pointed to by the intent inside. Okay. So that's why the pending intent are relevant. Again, this is the example from before. And again, just an example to rephrase what I'm saying so that maybe it's clearer. Basically, we have this intent that somehow is an explicit intent targeting the target activity, and let's assume it's is not exported, so it's private. And then you can do create a pending intent like this, and now whoever has penned has access to pen. So if I send around pen to application B, now this application B can start target activity. Okay, and again, starting activity may not seem as a bad thing to you in this moment. You just start an activity, but what if this activity actually replies back with something sensitive? Okay, now you see how this could be problematic. And a common mistake, so this could be security relevant already, but a common mistake is to create a pending intent with an intent that does not specify the target activity. So somehow what you can do is to create an intent with nothing inside, and then you create a pending intent that wraps this empty intent. This is very dangerous security-wise, because what happens is that there is a special rule, and basically if a receiving app receives this pending intent, you can access the intent. And now if this intent already specifies the target component or action, then I cannot do much. Either I do what this intent is specifying, or that's it. However, if this pending intent wraps an intent that does not specify anything, so it's empty, so there is no target component or target action, then the crazy thing is that let's say the receiver app can modify this intent. It can select which activity to target or which service to target inside, and then use it. Okay. So let's say you have this pending intent wrapping an empty intent, and this application A sends it around, maybe through a broadcast receiver. Now application B has it. What you can do is to take this intent, you modify it, and now you can basically interact with any arbitrary activity or component within the first application. Okay. Yeah. So you can just change this component. Again, if you specify the target component, then you cannot do this anymore, and application B can only start the target component. Now, one other question that usually comes up is, how can an attacker get access to this pending intent? Who is going to be so crazy to send it around? Well, there are at least a couple of scenarios. The first one is that you act as a malicious notification listener. Since apps, when they display notification, and since apps, when they need to somehow discuss and when apps need to specify what should happen when the user taps on the notification, they need to use pending intent. If you act as a malicious notification listener or manager, basically you are able to intercept this pending intent. And if you're able to intercept this pending intent, then you can do bad stuff. Okay. The second scenario is more generic, is where the vulnerable app basically mistakenly leaks this pending intent around. Sometimes you have apps that basically creates an intent and then they send this pending intent around, and now the receiving app has it because maybe this developer didn't really get the power of this pending intent. Or maybe sometimes you have people putting information in a broadcast receiver and then they send it around, and now everybody has access to this pending intent. So this stuff happens in real world applications. Here there is an example from a paper. This is not a paper of mine, but it's a very interesting one. Basically, they did a study on try to take an application and try to analyze it to find this kind of a pending intents, vulnerabilities, and again, this is an example from this paper. And here we can see how in this piece of code, basically there is an onCreate method. Okay, now you're creating a base intent that is empty. And now we're creating a pending intent which somehow wraps the base intent. Okay. And then what would happen in this proof of concept is that you basically talk to another application, you create an implicit wrapping intent that somehow as an extra, as in the bundle, you put this pending intent. So it's kind of confusing because you have the empty intent, the pending intent, and then you have the implicit wrapping intent that wraps all of this. And then basically this intent will be sent around. And any app that could intercept it could basically receive the intent, get it from the bundle, get the pending intent from the bundle, then modify the empty intent, the base intent in the pending intent, and somehow interact with this application, even with components that are actually not exported. All right. Yeah, so that's where the leak happens. Cool. All right. So again, I hope you're getting the point of these discussions. So a bunch of topics, and then these topics may not seem related to security, and then turns out they're actually related to security. Okay. So Now, switching a bit gears, we are going to talk about this man-in-the-middle thing, which is much more related to security. I mean, it's also other stuff is related to security, but in this one it's quite obvious it is related to security. I'm pretty sure you have heard about this term. If not, that's absolutely okay. If you did heard about this term around, please don't be confused. Sometimes there are people, there are different definitions, or people using some kind of, explain this stuff in a weird way, or maybe you never really studied this, but you convince yourself you know it. So please try to approach this with a fresh mindset. Okay, cool. So what is a man-in-the-middle attack and why it's relevant? And how it's practical, is it practical, and so forth. So first of all, we have a user and a website. The most basic man-in-the-middle attack is the following: with the user somehow access the internet, a specific website through the internet, and now you have an attacker in the middle that can do man-in-the-middle attack. Okay, so again, the goal of these slides is to explain how practical it is, what kind of different scenarios can lead to man-in-the-middle attack, and what can a middle attack actually do from the technical perspective. Now, if you check the details, so now this stuff can work, like, there is no actual cloud with question marks. That's not how the internet works. And there is no like red things on this cloud. It's more complicated. So let's try to be more specific on how this stuff actually works. So let's go back. We have users, and then we have a website. And to actually reach this website, there are a bunch of routers around the internet, and there are a bunch of links. And there are a number of ways that one could mount a man-in-the-middle attack. Moreover, there are, this laptop is connected through a cable, but of course it could be that this user is actually using the Wi-Fi, okay, and accessing to this router. Now, this Wi-Fi router, of course, is somehow attached in a way or another to the actual network. But of course, the user with this wireless car can actually reach directly the router. Okay. Now, a first step could be, a first way of doing man-in-the-middle attack is for an attacker to be somewhere on the network, or somewhere on the routers, or maybe on the direct connections from the the user's machine to the first point of access of the internet. Or, for example, it could infect the router, and it can control what you are, is on the path of your communication from user to website.com. It could also be another guy in somehow the same network. So maybe you are attached to a specific network, and there is an attacker. Well, in this context, you can also do man in the middle, or maybe you do man in the middle, or maybe you are on the same Wi-Fi. So this is a very classic scenario. It can be in a school. The attacker could be one of us, let's say, could be connected to the Wi-Fi, or it could be a Starbucks, and an attacker could stay there. Everybody's using the same Wi-Fi. So what I'm trying to say here is that all this man-in-the-middle attack material that I'm going to present now is relevant in all these cases. So whenever you go to Starbucks, you may be conceptually under the threat of man-in-the-middle attack. If there is somebody there with a malicious intent, could try to mount man-in-the-middle attack. Now, I don't want to be too terrifying. It's not that bad nowadays, because there are a number of mechanisms to prevent that the man-in-the-middle attack can be so devastating. So, the goal of these slides is to, try to remove the scary part and try to really understand how dangerous it is, and when it's dangerous, and why I can actually feel confident to go to Starbucks and check my emails on Gmail, okay, without worrying that people are doing man-in-the-middle attacks on me. Let's get to it. Okay, cool. So first of all, a couple of things. We can have two different kind of types of man-in-the-middle attacks: passive and active. The passive, the attacker just observes the messages without modifying them. Okay, so literally just see things and it doesn't do anything. You may not even know that the attacker is there. In the active case, the attacker actually is active. So basically what you can do is to intercept the messages and modifies them at his will. Okay. Also in this case, you may not even know that the attacker is there, because depending on how the modification happens, could be completely transparently. Okay, but again, you get the point, I guess. So before discussing the actual attacks, man in the middle is also interesting for reverse engineering. Let's say you have an application that somehow interacts with the network, and you would like to understand, how this application is interacting with it, or what kind of information is passing along, and so forth. So there are 3 steps conceptually that you can do to do this investigation. The first one is to take your device and configure it to use a proxy or gateway. And then you would set up a proxy on your laptop or wherever place that you control. And then you take this device or emulator, and then you tell it, please make all the connections go through this proxy. So the idea is that you have the device, and then the device will talk to your laptop, and the laptop then will relay your traffic to the internet. And so, everything goes back and forth. But at least on your laptop, you're going to see the full traffic and see what's going on and study what's going on. Now, I use this proxy gateway VPN terms kind of interchangeably. Of course, they're not all the same thing, but they share the same idea that all the connections go through a specific point, and then this specific point basically relay these connections to the final destination, then waits for the answer, and then relays the information back, etc., etc. But they're slightly different terms, so let's get to them. So a proxy usually it's somehow it's a kind of program that waits for connections to happen, and it knows that this goal is to take these connections and reopens them targeted to the actual destination, waits for the reply, and then reply back. Okay, and somehow the system, the device that you want to inspect, somehow it needs to know that there is a proxy. Okay, so somehow you set the proxy, and then so you tell the system, please set up a proxy, but the apps can actually usually choose to not go through it. So it depends on how it's implemented. But for example, on Linux, you can say, this is the proxy configuration, and then there are some applications that check this configuration setting and say, there is a proxy configured, so let me go through the proxy. But there are other applications that don't care, and so they would just bypass it. Okay. Browsers usually honor the proxy settings. So if you set a proxy on your, you configure your machine to use a proxy, Chrome, Firefox, all these browsers would actually check if this was actually set, and they would honor this. Or in a browser, you can say, please redirect everything through this proxy. This stuff is usually honored. Okay. But in terms of raw connections, there is no guarantee that this is going to be honored. The pros of this technique is that usually does not require root or any crazy low-level tricks. Okay, it's just some configuration setting. Once you do it, usually it's honored, but not always. Now, the other thing is this gateway and VPN. Again, I'm not going to go through what a VPN is and so forth, but the idea is that you have a point where basically all your packets go through independently, whether it's a specific protocol and so forth, or the app just sends things, and then these packets are redirected through this central point, which is called the gateway, and there is no way around it. Okay. I also mixing stuff up with a VPN, because usually if you take your device and you make it as a VPN, then all these packets are going to be sent to the VPN gateway. And so at that point, you can maybe do introspection and so forth. Okay. Again, depending on your configuration, you could basically set up a VPN. So everything that comes out of your laptop or your emulator or your device is going to go through the VPN gateway. Again, you can set it up on your laptop, on your physical phone. The gateway you can set up in your Wi-Fi connection. So you can say, sure, I'm connected to this one, but please use this IP address as the gateway. So every packet redirected to somewhere else, they're going to be routed through the specified gateway. Now, this gateway could happen to be your laptop. And so all the packets are going to be redirected to your laptop. Now, of course, your laptop should be properly configured to take these packets in, redirect them to the target destination, and act as a router. If you don't do this, you're going to receive the packets, but the device is never going to back a reply, never going to get back a reply. But so I'm just saying it's not super trivial, but this is clearly possible. And usually, depending on how you do it, this may require some advanced tricks. If you just want to modify the gateway, or if you can modify the Wi-Fi settings. If you want to access VPN, you don't need root. There are VPN apps. You can just access VPN, but you can also do this at a lower level. Basically, you can just do with IP tables and so forth. You can redirect all the traffic to a specific endpoint. And unless the app does some crazy stuff, there is no way around this. Cool. So in practice, how does it actually work? Okay, so for the emulator, it's actually quite simple. The emulator program accepts an argument or a command line option, HTTP-proxy, and you specify where the proxy is. Okay, and it's called proxy, but it makes all TCP connections going through this specified proxy. And if you have a real device, then you can install applications. One of them is ProxyDroid. It does some IP tables magic, and so a request route. He also uses native code, but I tried to actually run an emulator. I couldn't do it because it only runs on RAM. That was for an old demo. But again, there are applications out, but they may not be the super easy to use and so forth. Another one that I use is Shadow Socks. It's actually pretty good. I tried to set up a VPN. Actually worked quite well, and it does not require root, so it's pretty handy. Then going back a second, here I said, for example, you can set up the emulator with the HTTP proxy, and then you can tell the emulator, please go through localhost 8080. That's where the proxy is. How do we set the proxy? What I usually do is to use MITM proxy. So it's a program, again. You could make it run on your laptop, and then you set it up to start on localhost 8080 or to listen on localhost 8080. I think that's the default. And then basically that's how you point the emulator to this endpoint, to localhost 8080, and all the connections from the emulator are going to be redirected there. And as man-in-the-middle proxy is going to basically relay these connections back and forth. So from the perspective of the emulator just talks to this proxy and then expects a reply back from the correct target. From a perspective of applications inside the emulator, they have no idea what's going on, because this proxy thing is something that happens outside the emulator, okay, which is clearly not visible from inside the application. Now, of course, if you just in an application, if you just open a connection and access google.com and gets the reply, it's fine. It is going to work. But of course, this does not imply that it's impossible to understand whether you're going through a proxy or not. There may be a number of tricks. Maybe check the time to leave of the packets, or maybe try to put some weird data. There could be tricks. I'm just saying the presence of a proxy may be. It doesn't mean it's impossible to find. What I'm saying is that this stuff works transparently. I mean that if you have a normal client and tries to access something, then usually it's going to work. But it doesn't mean that the malicious app cannot detect that there is a proxy in any possible way. Okay. Again, managing the proxy is pretty cool. There are also some companion tools to play with it. Check it out. The professional tool is actually Barb. It's expensive, but there is a usable demo. You can play with it. Again, this is mostly for web security, but I've also seen people use it for reverse engineering Android apps. All right. Here it seems I'm changing topic, but I'm not. So again, the topic is man-in-the-middle attacks, and I want to demystify all this HTTP, HTTPS, and pinning, and which role they play within the context of man-in-the-middle attacks and how to prevent them. So, some history. HTTP stands for Hypertext Transfer Protocol, is the main protocol to interact with websites, okay? And you should probably be familiar with this, with HTTP : / and is not considered secure. So it's a basically clear text protocol. And if you use this protocol to access a website, such as our super secure www.s3.eurocom.fr, which I believe is still in HTTP, not HTTPS. What happens is that, literally your browser or your, browser on your laptop, browser on your phone, literally send out in clear text something like, I would like to connect to this host and I would like to get this specific page. Can I please get it? And the web server in HTTP will reply, sure, here it is. Now, if you go to this S3 Eurocom.fr website, it's not particularly sensitive, okay? And maybe you can think, oh, so if it's not particularly sensitive, why should I care if an attacker is seeing the content? Also, it's not that you need to log in or anything. So if the attacker is curious about what's going on this website, it can just go there itself. This is true. Unfortunately, that's not the end of it, and it's still dangerous, and this should still be fixed. So what's going on? So once you use HTTP, the communication is not encrypted. And I guess this is clear. So if you have an attacker doing man in the middle, and again, when I say attacker man in the middle, means the attacker could be somewhere on the network, somewhere on your network, somewhere on the Wi-Fi, and so forth. The attacker can see absolutely everything. Now, if you access S3 Eurocom.fr, okay, you're gonna see, I left Eurocom, but you're gonna still see my beautiful face, at least if you try now, but it's not super private. But I guess you can imagine now, depending on the website, then this could actually be sensitive or not. And believe it or not, I still remember when you could actually go to Gmail through HTTP and not HTTPS. Okay, so the first times I went to Gmail, I still remember the HTTPS, but there were some attacks where you could trick the user to go to HTTP gmail.com, and this would actually work. And in that point, basically, would log in Gmail in an unencrypted way, and this includes also your cookies and so forth. So an attacker on the network could actually see your cookies going, steal them, and somehow authenticate himself as you. Okay, so now this is not possible anymore. How did they fix it? Well, next slides are going to show it, but it's actually a pretty big deal. Again, vast majority of sensitive websites now are not using HTTP anymore, but there are still some that use it, and when they do it, it's very bad. Again, not encrypted means everybody on your path or on the Wi-Fi network, which again could be quite frequent, Starbucks scenario, can see everything. The other thing is that the communication is not authenticated, in the sense that not only I'm talking to S3 Eurocom and people can read it, but I cannot even be sure that I'm talking to the real S3 Eurocom. That's what I mean with the communication is not authenticated, okay? I don't have any guarantee that once I think I'm going to S3 Eurocom, I'm getting a reply from S3 Eurocom. This is not something that HTTP protocol can tell you. Same for, Facebook.com. If you go to Facebook.com and you happen to use HTTP, again, now you cannot do this anymore, but I still remember when you could do. You would have no idea. So you go to Facebook.com, and even if you type it yourself, it's actually Facebook.com, you would have no idea that you're getting replies from Facebook.com. So when you go to Facebook.com and then you see a website that looks like Facebook, if it's HTTP, you wouldn't know whether it's an attacker that tries to simulate that there is a page that looks like Facebook, but it's not. Okay. So if you go on a very sensitive website where you're supposed to put login, username, and password, and it's HTTP, you should be very, very careful about what you're doing and whether maybe something is wrong. And again, when I say man-in-the-middle attack, is nothing super complicated from the technical standpoint. Maybe it's tricky to be on the network path. I don't think it's tricky depending on the attack scenario, but for sure, it's easy to be a Starbucks and to attack everybody around there. Okay, so this kind of attacker is actually quite relevant and quite frequent that you potentially encounter attacks like this. And again, these attacks could be both passive and active. They could manipulate your traffic, put some code there, and so forth. Now, HTTPS. HTTPS is the same stuff, but it's secure. And is, again, the secure evolution of HTTP. And how do you know if you're using HTTPS? Usually looks like this. There is some kind of a green lock, there is not written, not secure, and so forth. And HTTPS has a number of great properties. First of all, the communication is encrypted with TLS. Okay, so once I go to docs.google.com, an attacker cannot read what is being transmitted. Pay attention that the request that you want to access docs.google.com is public. So even if you use HTTPS, if somebody reads your network traffic, is going to still see that you want to contact docs.google.com, because somehow you need to tell the website, which with which key to encrypt the traffic and so forth. With that being said, apart from this information, then whatever comes later on, it is private. Okay, you cannot read it, or you would see just the encrypted text, but you cannot really access the content. And the other very important point, which again, depending on the context, may be more or less relevant, is that the communication is authenticated. What does it mean? It means that if you see a lock next to facebook.com, or if you see a lock next to docs.google.com, you know that you are actually talking to facebook.com or docs.google.com. You're talking to the real docs.google.com or the real facebook.com. Okay, that's extremely important. This green lock or the Glock really gives you trust that if you're reading on your browser bar facebook.com, you're talking to facebook.com. Okay, and man-in-the-middle attack are not possible here. They can basically do denial of service, they can destroy your connection and so forth, but somehow they cannot really read what's going on, and they cannot really fake to be that they are real facebook.com. Okay, so if you see the lock, you know you're talking to facebook.com, and that's beautiful. Yeah. Okay, so one huge disclaimer, and I'm going to ask this in the exam, please, it's extremely important, don't be confused. And yeah, so if you see a lock next to docs.google.com, what it tells you is that you are securely talking to docs.google.com, but it does not tell you that docs.google.com is trusted. Same for Facebook. If you go to facebook.com and you see the lock, this tells you that you are securely talking to facebook.com, but it doesn't tell you that facebook.com is trusted. It's you, the user, that knows that the real Facebook domain name is facebook.com. Is you, the user, that knows that to actually go to Google Docs, you need to go to docs.google.com. But the fact that docs.google.com is the original site, that's not something that that HTTPS tell you. It just tells you, you think you're talking to docs.google.com, and I'm telling you, yes, you're talking to this guy. But I cannot tell you if this guy is trusted, is trying to impersonate Google. I cannot tell you anything, okay? And I think this is stuff from last year. I think at this point, more than 50% of phishing websites now use HTTPS. So somehow rephrasing it, there are some phishing attacks that basically use some kind of stuff like, peppa.facebook.com, no, not this one, or, realfacebook.com, let's say, and then you would say, and you see the actual log. You would imagine, okay, realfacebook.com, I see the log, must be safe. No, this means, the log means that you're just securely, where securely means encrypted and authenticated, you're securely talking to realfacebook.com. But if it happens that realfacebook.com is actually a malicious website trying to steal your password, you're still gonna fall for it, okay? Again, the log does not tell you if it's safe to put your password in. It just tells you that the website that you see in the address bar is the one you're talking to. All right, Sorry, I need to repeat this tons of times, but it's a huge mistake that several people do also, in the community, and they are an embarrassment. And I want to do my best to make sure that once you get out of here, you actually remember this and you don't get fooled. Okay. Now there is another thing I want to discuss, and it's about HTTPS certificates. So one question that I guess popped out is, okay, let's say I go to facebook.com. Let's say I get the lock, but the lock is something shown by the browser. Okay, so if I see a lock, is the browser that knows that my communication with facebook.com is actually safe. It's encrypted and it's authenticated. But how does the browser actually know that I'm talking to the real facebook.com? That's where HTTPS certificates kick in. So somehow there is a chain of trust, and this is the short one-liner. I'm going to explain it better. But basically, there is a chain of trust, and until a root certificate says, we start from a point, from Facebook telling us, I've been signed by this, and we keep following the chain, and at the end, if we end up at the root certificate, this is going to tell us it's okay. I've been making a mess explaining this, but I have next slide on this, so I'm still calm, no panicking. So the idea is that once you get a reply from facebook.com, this is basically, it's a reply and it's somehow signed by a certificate. And the question is, how can I know if this certificate is to be trusted or not? Well, usually this certificate comes and then it says, okay, I'm certificate ABC and I've been signed by this other certificate. Then the browser can say, okay, let me say this other certificate XYZ. Checks, the certificate XYZ says, shows that is also signed by certificate DEF. And then the browser says, okay, let me check this certificate DEF. It checks it. And then it keeps doing this. And the hope is that at a certain point, one of these certificates in this chain is going to be signed by a so-called root certificate. So the idea is that browsers in general embed a list of trusted certificate authorities within the browser themselves. And these are hard-coded things that the developers of these browsers, ship the product with. And the rule is that if you have a communication that is signed by certificate, which is signed by another certificate, which is signed by another certificate, which is eventually signed by one of these root certificates, then you're considered as trusted. And if you're considered trusted, I'm going to show a lock. If you're not considered trusted, in the past you will see maybe a red lock. Now, depending on the website, you basically get killed. You basically, the browser refuses to let you go to the next page. Okay, it tells your connection is not secure. Pretty sure I have another slide on this. So again, there is a chain of trust, and I'm trying to rephrase what I just explained in the previous slide. The way it works is that Facebook generates a certificate, public key. Certificate is the public key plus the meta information, but it generates like a key pair, and then Facebook has a certificate authority to sign it, to sign this, public key metadata combination. And then ideally the certificate authority says, okay, who is I'm talking to? Okay, this guy is trying to make this, is asking me to sign this certificate. Should I do it or not? And maybe it says yes, maybe it says not. But the point is that even the certificate authority has its own certificates that are signed by another certificate authority. Okay. And eventually, this kind of certificate authority that signs another certificate authority and so forth builds somehow a chain of trust. Okay. And again, when do you stop? When you're signed by a root certificate. So once again, browsers have a list of certificates they trust, and these trusted ones constitute the root of trust. And you're trusted if eventually the chain ends up in one of these root certificates. Otherwise, if that's not the case, then you're not trusted. So can you do this man-in-the-middle attack when you're using HTTPS? Well, if you actually use HTTPS in a proper way, the answer is no, but HTTPS makes app analysis more difficult. So if an app uses HTTPS, it's a bit trickier. But if you set up a proxy, that's not enough, because sure, the connection is going to go to the proxy, but you're not going to be able to read anything. Okay. You see the integrated drafted, but in this context, when you try to reverse engineering applications, you are the owner of the system or the owner of the app, or at least you can modify it. So can you do something about this? Can you modify your system so that you can see what's going on? And the answer is yes. So the first trick is SSL strip. This is actually a trick that worked well outside the mobile environment. It's some sort of a downgrade attack, where basically I do a request to facebook.com in HTTPS, and this connection, let's say, is routed through me. I'm the attacker, and in theory, I just see HTTPS, and then I should reply to HTTPS with Facebook, and then I get the back reply. Sure, I'm the man in the middle, but I'm only seeing encrypted stuff, so I don't get anything out of it. Well, in this SSL strip attack, downgrade attack, the idea is that I receive a request to HTTPS to facebook.com, and what I do is to rewrite packets so that the request was to HTTP facebook.com. In this way, basically, I open a connection to facebook.com, I redirect it, and then the user is going to see, sure, facebook.com, but it's not going to see the lock anymore. At the point in time when this attack was proposed, there was no prominent warning with the non-secure. If you have HTTPS, you will see the green lock. If you didn't have HTTPS, then you wouldn't see anything. You wouldn't see non-secure. So the idea is that you go to facebook.com with HTTPS, but then the attacker downgrades you to HTTP, and you wouldn't notice. And so you put username and password, and these are sent in clear to the attacker and then to Facebook. Now, again, there was a tool released. It was a very cool attack, but there's a counter trick that is the defense that people now implemented. So the defense is called HSTS. It stands for HTTP Strict Transport Security. And the idea is that the website tells the browser from now on use only HTTPS or refuse HTTP. What does it mean? Let's go back to the example of facebook.com. You have the user that goes to facebook.com with HTTPS, okay? And in this case, the attacker would downgrade the connection. So it would say, you know what, let's go to HTTP. In this case, basically, so scratch what I said. Let's say that we start with a scenario where at the beginning there is no attacker, okay? So the user actually goes to facebook.com, there is no attacker. So you go to facebook.com, and then the connection reaches facebook.com, and then facebook.com would reply in HTTPS, but it would also add, you know what, everything is fine now, but please keep in mind for the next time that me, Facebook, I will never, never, never talk to you in HTTP anyways. So please refuse any attempt to talk to facebook.com with HTTP. Always use HTTPS. If there is an attempt to downgrade to HTTP, please don't trust it. There is an attack going on. Okay, great. So if you do the first time, after the first time, if the first time is legitimate, now the browser knows that, hey, facebook.com asked me to use HSTS, which means asked me to never use HTTP. And now this as a strip attack doesn't work anymore, because at the second time when there is an attack, that the browser tries to go HTTPS, the attacker tries to downgrade to HTTP, but the browser now says, Facebook in the past asked me to never use HTTP. Bam, the attacker is gone. Okay, so that's pretty good. There actually, this HSTS could be abused for privacy. It's depending on which websites, if there are some websites that says all the time, please do not use HSTS, please use always HTTPS or not, then depending on whether a given website already is okay with the downgrade, if this user has already visited this target website in the past or not. It's a very interesting privacy attack. There is a link there. Check it out if you're interested. But there's not a big deal. The problem of this HSTS at the beginning was that you need to trust the first connection. If you go to facebook.com at the first time, and during the first time there is an attacker, then this HSTS will not kick in. This current solution is that nowadays, for many of these very, very popular domain names, there is already a list loaded in the browser that says, for this facebook.com, google.com, gmail.com, instagram.com, whatever it is, always use HTTPS without waiting that the server tells us to use HTTPS. And in this case, this kind of a downgrade attack is solved. The second trick is that what you could do as an owner of the device, you could add a trusted certificate to your system. Again, this is both for your laptop and for your device. What does it mean, trusted certificate? Well, it means that you would tell the system, system, I know you have a bunch of root certificates that you trust, but please also add this one that I give you to the trusted list. And in this way, what you could do is to somehow, now that you trust this stuff, somehow maybe, there are some powerful attackers that could obtain a valid certificate for, facebook.com, signed by this new trust certificate, and sorry. So if this trust certificate comes from me, what I could do is to sign or self-sign or sign this facebook.com with this trust certificate, and then I give you this, and then now this is trusted, and so the browser is full. Okay, so of course it depends on if I need to manually add a trust certificate, then basically I can create a certificate myself and then use it to sign your thing. But of course, there are some powerful attackers that could compromise legitimate certificate authorities. What is a legitimate certificate authority? It's a certificate authority which has some certificates that are signed by another certificate authority, which are eventually signed by a root certificate. If an attacker is able to compromise a certificate authority that is already on the root of trust, on the chain of trust, then I will be able to create a new valid signature for facebook.com with a certificate authority that is already trusted somehow. Okay. The counter trick for this is that they came out with SSL pinning. So somehow SSL pinning is the principle is very simple. Not only the browser checks that facebook.com is signed by certificate, which is signed by certificate, which is signed by certificate, which is signed by a rooted certificate. Sorry, a certificate in the root of trust, but it's checking that is actually signed by very specific certificate, or basically a certificate. This certificate needs to be on the chain. Okay, so somehow instead of saying trusted or not, it said it needs to be trusted, and it needs to be trusted going through a specific certificate. And this helps because now as an attacker, either I manage to compromise this specific certificate, or if I manage to sign facebook.com with another certificate, even if it's trusted, is not enough because SSL pinning would reject my connection. So again, an example, you could say, I would expect google.com. So SSL pinning would say, I expect google.com public key to be ABC. And if I connect to google.com and it's signed with XYZ, I refuse it, even if XYZ was actually considered trusted. Now, in the context of mobile phones, how do you use HTTPS? Well, it's as easy as this. You just create a new URL with HTTPS, and now everything works out of the box. And the attack here could be to install a custom certificate. That's what I mentioned before with adding a trusted certificate. And now basically, since you are adding a custom certificate for which you also have the private key, you can basically forge valid SSL certificates and do man in the middle. And again, there are documentation of actually doing this. This stuff actually works and it's practical. And again, from the app perspective, what you could do again is the equivalent of SSL pinning on the app side, okay? Where instead of just saying, oh, this HTTPS needs to be signed with a trusted certificate, no, in this case, you would specify this wikipedia.org should be signed with this certificate, not just a valid one. Again, same principle. So for mobile, there are different ways of implementing this. One of the main one was to create a custom trust manager, and basically with this trust manager, you would manually check which certificate is used, and you can check it against a blacklist. And again, if the certificate is not one of the few trusted, then you raise an exception. There is an attacker counter trick, which is, if you have access to the app, what you would do is to modify the app so that you basically bypass the check. And again, that's the classic trade-off. There's a classic harm race. If an attacker actually can modify the app, you can use obfuscation and so forth, but the attacker still has a way to tamper what's happening on your application, and maybe it can win in this way. There are also some tools that popped out. One is this universal Android SSL pinning bypass with freedom. It's a cool one, but try to get this kind of tools with a grain of salt. For example, is this really universal Android SSL pinning bypass? Probably not. In a sense that the way to bypass this, the generic thing is that if you see Trust Manager, maybe you suppress an exception, fine. But SSL pinning is something that it doesn't need to go for sure through an API, right? You just need to do some kind of HTTPS connection and then somehow get a reply with signed by some certificate, and then you would check if this certificate is signed is one of the entries that you're trusted. But of course, you could do this check in many different ways. You could go through native code, you can obfuscate them, and there is no way you can do this kind of super generic universal SSL pinning bypass. So please pay attention to when you read these titles. Sometimes they're a bit misleading. Exactly. For example, in this case, the check could be done in native code, and good luck finding it with it. Okay, so there have been security protections to prevent or to make sure the user is well informed about something weird going on their device. And for example, in previous versions of Android, if you would add a new custom certificate, you will get a device monitoring warning, basically saying prominently as a notification, pay attention because the user is potentially, you are potentially being inspected. Your network traffic could be potentially inspected. And so the user would at least have a warning about this topic. And I think at that point, it would look like this. Again, this is the ancient. Starting from Android 7, user certificates are not trusted by default. So even if myself as an attacker would add a trusted certificate to the Android device, still it will not be trusted, okay? And another interesting thing about Android security and related to this HTTPS topic is that they changed the clear text network policy. So in Android 6, what they did was to introduce this strict mode to make sure the app does not use clear text. And so you as an application developer could set up this strict mode to make sure that no matter what, your app doesn't actually use HTTP, maybe because you forgot some HTTP URL, you want to make sure you don't use them, you just use the strict mode. In Android 9, the Android developers, the Android security team, change default so that all clear text traffic is actually blocked by default. And this actually created problems with my challenges because, when I started this class in 2018, this stuff was not the default. So you could do clear text. And so at the beginning, students could do, connect to http google.com, for example, or, HTTP, another website, or my own, local IP that was with HTTP, and everything would work. The year after they introduced this, I changed the emulator that now uses Android 9, and now this test case would not work anymore because by default, all HTTP connections are blocked. So Of course, it's still bypassable. You can basically get access to the strict mode and modify it and somehow allow this clear text traffic to go through. But of course, you get the idea. Like, Android developer and Android security team, by changing the default, is trying to push the entire community to move towards HTTPS everywhere. And the latest, news from the Android security world related to this HTTP, HTTPS is the network security policy. Give me a second. All right. So this network security policy, which is somehow a way for an application developer to specify what the security policy should be. And this security policy somehow can enforce things like this domain connections to domain X should always be accessed with HTTPS. So somehow, instead of having just the clear text allowed or not allowed, it allows developers to be much more fine-grained. And so maybe there are some sensitive domain names that you really want to make sure you don't access to through HTTP. So you would deny clear text policy for these domain names. And maybe there are some legacy domain names that should be still accessed with HTTP. Then you could allow clear text for only these ones. And you can also specify sets of certificates for SL pinning, and you can specify which certificates to trust and so forth, which is great. The cons is that for reverse engineering, if you have all the security checks through this network security policy, you just have a file that you can quickly modify, and you can bypass some of these mechanisms quite easily. So in concretely, let me move. From the concrete perspective, network security policy is an XML file, and it looks like this, where you can say what's the base config. You can say clear text traffic permitted, true or false, and so forth. What this slide is showing is the default network security policy, depending on the API level. So between 24 and 27, this was it. So clear text traffic permitted was true, so you could still access HTTP by default, and you would trust certificates belonging to the system. Let's say key store. System key store is basically the trust certificates by default. If you check the recent versions of Android, basically the HTTP now, clear text traffic now are not permitted anymore by default. Again, this is the default one, but you can create your own, and you can basically tweak this value, so you can still enable it. But again, this is the default. And again, they changed it so that HTTP is not allowed by default anymore. And it's interesting to see how in the very past for Android up to API level 23, this was the network security policy that was adopted at the point where HTTP was enabled, and also they would trust by default certificates belonging to the system key store and to the user key store. Again, the system key store, as I said, is the key store collecting all the certificates that are basically the trusted ones. And the user certificate, the user key store, is the key store containing certificates the user added manually. And so it's interesting to see how in these old versions of Android, these certificates added by the user would actually be trusted, although you would see the warning. But in the recent versions of Android, these certificates that the user trusts manually and adds manually are not trusted anymore. So even if you add them as please trust this, the application would ignore it. Again, this is just an XML file, you can modify it and so forth. But again, this shows, first of all, there is a network security policy, which is a new technique new configuration policy to basically set the network security posture of your application. And then the idea is that Google is really trying to push all these apps to move to using HTTPS everywhere. That's what Google has been trying to do for a while in the web world. They're trying to do the same for the mobile app. Of course, it's a great initiative. And our impression is that we're still a bit far from that. We had a recent paper from related to a student where we basically studied how a lot of applications would use this network security policy, if they would modify it, how they would use it, and so forth. And we found out that many apps are still somehow allowing clear text policy, and they're doing a number of other mistakes setting up their network security policy. Again, encouraging results in sense that we are getting to a better position where many more apps are using HTTPS, but we're not there yet, as we try to convey with the title of the paper. And I think that's about it for today. I know it's a lot of content. As always, my email is always there, so please feel free to shoot me an email and answering questions. And if something is not clear, I may even update the slides and so forth. With that, I wish you all a good week, and I'll see you with a new recording next week. Bye-bye.